Latches and flip-flops are the building blocks of computer memory. In this particular video, we'll focus on the so-called SR latch. Later, we'll see how this circuit can be enhanced. The set-reset latch, or SR latch for short, can be thought of as a 1-bit memory. It can be put into one of two stable output states, triggered by an input pulse. The circuit remembers this state until it's changed again by another input pulse, or until the power is removed. For this reason, the circuit is known as a bistable latch. Before we consider the construction of SR latches, let's remind ourselves of some fundamental logic gates. This is an OR gate, and this is the truth table that describes its behavior. Any combination of inputs A and B results in a 1 at output P, except when both inputs are 0, in which case the output is 0. This is an AND gate, and this is the truth table that describes its behavior. Any combination of inputs A and B results in a 0 at output P, except when both inputs are 1, in which case the output is 1. If we modify the output of a regular OR gate by inverting it with a NOT gate, then we can swap the 0 for a 1 and the 1s for 0s in the output column of the truth table. In a similar fashion, we can invert the output of a regular AND gate. Then we can swap the 0s for 1s and the 1 for a 0 in the output column of this truth table. Each of these gate combinations has its own name and its own symbol. They are known as the NOR gate and the NAND gate. The NOR gate only produces an output of 1 if both of the inputs are 0. The NAND gate only produces an output of 0 if both of the inputs are 1. The SR latch can be built using one of these two basic building blocks. Let's start by considering an SR latch built from NOR gates. In this NOR gate version of an SR latch, two NOR gates are connected together in such a way as the output of each NOR gate is one of the inputs of the other. This cross-coupling of two gates results in a form of positive feedback. SR latches, like all electronic circuits, require power to work. The power connections aren't shown on this diagram. The SR latch has two inputs, R and S, and the output Q. The SR latch also makes the inverse of the output available. On this diagram you can see not Q, a Q with a bar above it. The starting state here is that S and R are both low, that is, both inputs are 0. Q is high, that is, the output is 1, and not Q, the inverse of this, is 0. Both of the inputs of the top NOR gate are 0, so the output of the top gate is 1. This is exactly what you would expect from a NOR gate. The inputs of the lower NOR gate are 1 and 0, so the output of the lower gate is 0. Because Q is 1, the latch is currently storing 1. Now we apply a pulse to input R to reset the latch. This changes the output of the top gate, and then this is fed back into the lower gate. The lower gate's output also changes, and this is fed back into the top gate. The pulse that was applied to reset the SR latch is then removed, and R is 0 again. But the output at Q is now 0, so the latch is now storing a 0. In order to store a 1 again, a pulse must be applied to input S, which will set the latch. Again, notice how the various changes are propagated around the circuit. The set pulse is then removed, and the circuit is now latched into a set state. It's storing a 1 again. Notice that if another set pulse is applied, it has no effect. Applying a set pulse at S will always force the latch into a set state, regardless of the previous state of the latch. Similarly, applying a reset pulse will always force the latch into a reset state. It should be noted that S and R are never left high. That is, neither is ever set continuously to the value 1. The latch is controlled by pulses only. This gives us an unusual looking truth table. When both S and R are set to 0, Q may be 1 or it may be 0, depending on the previous state of the circuit. Let's examine the truth table as this SR latch is reset again. The reset pulse is applied. S is 0, R is 1. Output Q is 0 and its inverse, not Q, is 1. The SR latch is storing a 0. The reset pulse is removed. Both S and R are 0 again. Output Q remains at 0 and its inverse remains at 1. The SR latch is still storing a 0. A set pulse is applied. S is 1 and R is 0. The output Q becomes 1 and its inverse becomes 0. The set pulse is removed. S is 0 and R is 0. Output Q is still 1 and not Q is, of course, 0. Now, the only circumstance we haven't considered is when both inputs, S and R, are set to 1 at the same time. If this were to occur, we'd be telling the SR latch to set the value of Q to both 1 and 0 simultaneously. In reality, Q would become 0 and not Q would also become 0. This would sort itself out if one of the inputs fell to 0 before the other. For example, if R fell to 0 first, with S still at 1, then Q would become 1 again. If, however, both inputs were at 1 and both fell to 0 at the same time, we'd have what's known as a race condition between the two gates. They'd be racing each other to feed back their new output, and it's impossible to know which one would win. Hence, if both inputs are high, the next state of the latch can't be determined. This is not a state that the latch should ever be in. It's illegal. It's invalid. Most of the time, inputs S and R should both be at 0, and only momentarily will one or the other input become 1. And at any time while it's operating, the SR latch should either be in a set state or a reset state, with Q and not Q the opposite of each other. One final piece of terminology. This type of SR latch is said to be an active high SR latch, because the normal condition for S and R is low, and a high pulse at one of these inputs is required to bring about a change. Now let's consider an SR latch built from NAND gates. Here's a reminder of the NAND gate truth table. Only when both inputs are high is the output low. The wiring of this SR latch is the same, but notice that input S is at the top now and R is at the bottom. Here's a truth table for this variation of the SR latch. It's a little different from the truth table we've just seen because this latch behaves differently. The difference is that R and S are kept high most of the time. Here we can see that output Q is 0, so the latch is storing a 0. When input S is made low momentarily, that is when S becomes 0 and R is still 1, the output at Q becomes 1. The latch is now storing a 1, and S can be returned to its normal high state. When R is set low momentarily, the output at Q is changed to 0. R can then return to its normal high value, and the latch is now storing a 0 again. An SR latch built from NAND gates, like this, is more explicitly known as an active low SR latch. An SR latch based on NAND gates also has a forbidden state. That is when both S and R are simultaneously 0. This would result in an illegal state in which both Q and its complement are 1. To summarise then, an SR latch can be built from NOR gates or from NAND gates. Both types of latch do the same job, but they're just controlled in a slightly different way. The NOR gate based SR latch is set or reset with high logic. That is, it is an active high SR latch. The NAND gate SR latch, on the other hand, is set or reset with low logic. That is, it's an active low SR latch. Let's consider a particular application of an SR latch. When a mechanical switch is pressed, it may actually generate several electrical signals in a tiny fraction of a second, when only one signal is required. Lots of on-off signals like this could then cause problems with the circuit that this switch is supposed to be controlling. The effect is known as switch bounce. An integrated circuit with an SR latch on it can be purchased commercially to allow clean interfacing between a mechanical switch and the digital circuit it's controlling. Here we can see a switch that will connect input S, which is currently high, to earth, making it low, and thereby changing the output of this NAND-based SR latch from low to high. This SR latch will ignore any further set signals after it's already been set, so it's serving to debounce the signal from the mechanical switch. You can imagine other systems which might make good use of this debouncing effect. For example, a burglar alarm may be triggered when a window or a door is opened, but we don't want the alarm bell to stop ringing if the burglar shuts the door. On its own, an SR latch has a few uses, mainly in control applications where we need to monitor some condition that might change or change back again and react accordingly. But more importantly, as you'll see later, the simple SR latch is the building block of sophisticated memory circuits.